And Thore will show us a little bit about database encryption in general, but we'll also present a little bit the new integration into MariaDB. Thore, please.
Thank you, Roberto. Yeah, and before I came to Securosys, I actually was at Six Digital Exchange, so I know both sides. I know what it's like to run them, HSMs, but also now I see all your customers' requests. I see the integrations. I'm trying to help you. So today, the session will be about database encryption, and it's split into two main parts. Okay. In the first half, I want to talk about the general concepts behind database encryption. What are the benefits? What are the limitations? And then the second half, I want to spend on walking through an example of MariaDB, which is one of the recent integrations that we did, just to kind of get a feel of what it would look like. And then the other databases are similar but different, but not too much. Before I start, I also wanted to give an overview of the integrations that we have. So today you can already find documentation and guides on our documentation website for MariaDB, MySQL, SQL Server, and Oracle databases. And also in the future, once we have KMap available as an API integration with the Primus HSM, it will also be possible to set up database encryption with MongoDB. So if you're interested, come talk to me, come talk to any of our staff. So in terms of concepts, generally we can split database encryption into two main categories or two classes, which is client-side encryption and server-side encryption. And it does what it says. So on the left, we have a database server, some Linux machine running my MariaDB or MySQL somewhere in a data center in the cloud. And we have a client that is accessing the database. So either a desktop application, a web application, or some other backend service that uses a database somewhere. And like the names imply, in client-side encryption, the client has access to some keys and it encrypts the data before sending it off to the database server. Whereas in server-side encryption, the client is not modified in any way. It does its normal queries, normal inserts to the database so that the database still sees the plaintext, but then it can operate over the plaintext as well. And then before storing it, the server will encrypt it. So this is, you will probably also know it under the name encryption at rest. So you would also combine database encryption with encryption in transit. So you do TLS there, you would have access control. You would, well, somewhere you will also have an HSM for more physical security. So database encryption on its own is not a magic solution. It also needs to be combined with with a risk assessment and controls. Yeah. So if we look at it in more detail, if in the case of server-side encryption, because the data is just sent to the server in plaintext, the server will have the data available in plaintext, but once it saves it to disk, it's encrypted, usually symmetrically in some shape or form. Whereas in client-side encryption, the client gets to decide what it encrypts before sending it to the server. So in this example, the application decided that the Unix timestamp and the username are not that relevant and can be sent to the server. So there you generally the way it's done is that you have more flexibility. For example, in Microsoft SQL Server, you can explicitly choose the columns that you want to encrypt before sending it to the server. And you could also combine the two. So you could still throw server-side encryption at it as well. Yeah, so in server-side encryption, you could start with doing full disk encryption, which is not database encryption itself, but it's encrypting the entire file system, including the files that the database uses, because in the end, the database management system is using files on the file system somewhere to store the data, and it's just building magic and indices around it to making data queries fast. But also in cloud databases usually have their own bring your own key mechanism and integration with the respective cloud provider's key management system. And all of the on-premise databases also have some configuration and setup thingies that enable you to use database encryption at rest. The advantage is that server-side encryption is relatively straightforward to set up. So if you know your way around a Linux command line and following a guide, it's usually just a matter of installing some extra dependencies, so setting up configuration files and pointing things in the right direction. You don't need to know much Like you need to know basics, like what the different algorithms are and what and even that you don't need to configure an algorithm. It's just there out of the box, but it helps to understand with risk assessment. Security-wise, server-side encryption protects you against someone who's able to take snapshots of the disks, or just also at the end when you're decommissioning servers, someone who is able to take the disk from the dumpster. But it does not protect you against someone who is able to take a memory dump, because while the database application is running, the database data is there in memory. So also someone who can execute your code with privileges, like your database administrator, would be able to see data. In client-side encryption, what you do is you have to change the application, or at least the database driver on the application, to be able to support encryption before it sends the data off. So this is an advantage. It works with any database if you wanted to, but it can also be more work. But you gain this flexibility of choosing what exactly you want to encrypt, what algorithms you want to use. So in these examples, Microsoft SQL Server has this always encrypted module where you modify the database driver and not the application. Whereas in PostSQL's case, you would need to modify the SQL statements. But you could also imagine that you modify your Java or Node.js backend code to use some other crypto library to encrypt stuff before giving it to raw SQL. And another disadvantage is that obviously, because the database no longer sees the data that you're sending to it, it can no longer help you in optimizing the indexes, the searching, or the aggregations, the joins that you would usually do on the data. So you would then need to ship all the data to the client again for it to be decrypted and then operated on. Two additional advanced things that I wanted to at least mention is searchable symmetric encryption and homomorphic encryption, which have a relatively low, 10 plus years of history in the academic literature and the startups building in the space. But with MongoDB is a notable exception here. I think in 2022, around that time, they launched queryable encryption. But other than that, none of these mainstream databases like MongoDB, like MariaDB, like Oracle have such features. But I think they're worth mentioning and looking out for in the future. So generally, to conclude the concepts section, is that the advantage is that you're encrypting the data at rest when you're storing them, either on-premise or in the cloud. Maybe you also have to do database encryption because some regulator tells you have to do this and you don't get a choice. But also maybe you want the ease of mind when you dispose the hard drives at the end. So in your enterprise context, yes, you can give them to someone who will physically shred them. For example, at home, I don't have the money to give them to someone, pay to someone to shred them. So because I have an Nextcloud server at home with a terabyte of data, and because of full disk encryption, I know I can just bring it to the recycling station. I don't have to care about my photos being leaked by someone because I will just throw away the key and it's fine. But then you're combining it in an enterprise with, you have full disk encryption, you have multiple layers, you have the physical destruction. But another limitation for both server-side and client-side encryption is that someone who has legitimate client access can still access the data. So if you have a SQL injection in your web application, that's legitimate, like it's using the legitimate path to the database, so database encryption does not help you. Also, you need to consider that the database does not just consist of the table data itself. There's transaction logs for consistencies, there's caches, there's all other kinds of logs. So you need to, for your specific database, you need to look at what stuff apart from the tables is this data, or what data is the database generating, where is it storing it, can the database encrypt it? For example, with MariaDB, you can encrypt all these things, but you need to turn them on individually. And this just differs, and you need to look at the database documentation and make a decision of what you want to do. So this was the first high-level part about database encryption in general. And now I want to walk through MariaDB, a specific example. The reason for this being that this was a very recent integration we did in July, August, hence the motivation for this talk. So in the architecture of this, we have MariaDB on a server somewhere on this side, and here we have a Primus HSM. And the new part is this plugin in the middle. And the job of the plugin is to translate between MariaDB and the HSM. And towards MariaDB, the plugin communicates via a C API or an encryption plugin API that MariaDB defines. And towards the HSM, we use the REST API, because this then allows us to use the transaction security broker to use keys that are protected by smart key attributes with this whole approval workflow, but also just normal keys. So if you don't want to use smart key attributes, this doesn't apply, and it just goes directly without any workflow automation. So what this plugin does is that MariaDB will ask, hey, I have some tables to encrypt, please give me a key. And then the plugin's job is to figure out the whole key management history of going to the HSM, getting a key, and giving it to MariaDB. So MariaDB defines this plugin API, which very condensed and simplified looks like this. MariaDB will say, well, plugin, please give me a key with this key ID. And then the plugin will return a data key that the MariaDB will then use to encrypt. And we will look at more details of how the keys are structured. The key hierarchy looks like in the next slides. From the point of view of the database administrator, it's also very straightforward. You just load the plugin, you tell InnoDB, which is the storage engine underlying, or one of the storage engines underlying MariaDB, please encrypt the tables. And then there's also InnoDB underscore encrypt underscore logs, where you can configure more things. Similarly, as a database administrator, you cannot just encrypt all the tables, but you can also encrypt specific tables and configure the key ID. So this is then what allows you to do key management, that you say, well, I have these tables, which I don't want to encrypt because they don't contain customer data. And then I can encrypt different tables with different key IDs, which will end up as different keys on the HSM, or somehow different keys on the HSM. So internally, the key hierarchy looks like this. On this side, we have all the stuff that is relevant, managed / owned by MariaDB. And on the left, we have everything that's managed by our new plugin. So here we have the data that is stored in the tables. And then MariaDB will generate a symmetric tablespace key for each table that is used to encrypt the tables. And this is fully in the scope of MariaDB as a plugin, whether it's a Securosys plugin, it's an AWS plugin, HashiCorp plugin. There's nothing we can do. This is just inside MariaDB. And then in the middle is what the plugin API of MariaDB defines, is that MariaDB will ask us, hey, please give me a data key with this key ID. And then towards the left, the plugin this is all in implementation detail of us, and AWS or HashiCorp plugin would do it differently, is that we need to figure out how do we want to manage these keys to, in the end, be able to give a data key to MariaDB. So the data keys are symmetric, and then the end on the left, we have the root key, and in the middle, we have the wrapping key. So when the database boots up, when the database boots up, it will load the plugin, and the plugin will try to go to the HSM to load the wrapping key and decrypt it with the root key. And the root key could be an SKR key, in which case you would get an approval. Do you want to unlock the database? Yes or no? And then once the plugin is loaded and it has the wrapping key in memory, it will keep this wrapping key decrypted in memory to be able to service any other requests that MariaDB has. And then at runtime, MariaDB could go to the plugin and be like, hey, the database administrator just created a new table with key ID 100. Please give me this key. And if the key exists, the plugin will give it to me, decrypt it, and give it to MariaDB. Otherwise, it will generate it. And all of these keys, so the root key never leaves the HSM. This is kind of the normal HSM key that you know. The data key and the wrapping key have to leave the HSM and be loaded into memory of the server that runs the plugin in MariaDB, because as a design decision, we don't want to get a notification for SKR every time MariaDB wants to do something. But there we decided that only upon boot once, similar to how you would unlock your HashiCorp vault once it boots and not every time someone accesses the key. But these are also stored on the HSM as data objects. So from the view of the HSM, these are opaque blobs, but the plugin still generates them using the randomness from the HSM and then stores them again back to the HSM. So you don't need any additional storage on your machine. Installation-wise, it's straightforward. You need an HSM, you need REST API and a MariaDB. Then for the plugin, you just download the shared object, put it on the database server. And then you have to configure the plugin to tell the plugin, hey, where can I reach the REST API? Which partition should I use? How can I authenticate against the REST API? And similarly, then you configure MariaDB to load the plugin and tell MariaDB which tables it should encrypt. And if you want to know more, you can go to our docs page for a detailed walkthrough and commands and everything. Yeah, so this is again the summary slide of the integrations that we have. I showed you MariaDB. MySQL is very similar because MariaDB is just a fork of MySQL. And yeah, SQL Server and Oracle also exists. Yeah, so this was a quick run through. Yeah, we have 3 minutes for quick questions. Otherwise, you can come find me later.
Thank you, Thore. Any questions? All unclear? Please turn up.
You actually need the root key, or could you just use it with the route?
So the problem is that Securosys Primus HSM does not support SKR on symmetric keys.
Oh,
So if we had SKR on symmetric keys, you might be able to use one layer less. But yeah, that's one reason. And SKR keys cannot be extracted. So I think even if we had our SKR here, we would need an additional layer because with this design decision that the plugin has to be able to service requests.
you just extract the data keys.
Yes,
So
but if the root key of if an ASA SKR key existed, SKR keys can never be extracted. So we still need the intermediate layer, unless we want every single decrypt of a new data key to be approved by an SKR. No, which is doable, which is tangible, it would be changing the design.
If you encrypt the memory of the database, what is the performance impact if you do views and queries on a database? Because every time has everything to be decrypted for an access, or
I don't know the performance numbers. I would need to ask our engineers.
But it doesn't need an HSM connection, right? You don't have to make it for it because it happens all local.
you, but you have to decrypt all the
Absolutely.
data to
Yeah.
some queries and views.
Absolutely.
Other questions, Thore? Hans, you ready for the demonstration? Thank you very much.